speak on Ron's conference, but I guess, well, happy birthday, Ron.
In that sense, yeah.
Yeah, I'll tell Ron's influence. I was his student in the 90s. Penn, so I came to Penn and I didn't really want to know what I want to do. So I went to his class and algebraic geometry, having no knowledge whatsoever about algebraic geometry. So I liked it and said, oh, I want you to be my advisor. So a couple of years later, so he gave me a book, Johann Kaprano-Televinsky, and said, read it, and so I read some part of it. So there is this amoeba pictures in the book. You see the book. So that time, Strominger-Yau-Zaslow conjecture came up very hot topic, and so he said that so put yourself in the middle of this hole. If it's a labial, there is one hole in the middle, so put yourself in it and just look through, and then you see the Strominger-Yau-Zaslow. That's essentially what my theory is. And I'm still in this hole. I mean, not in this hole anymore. You walked a little bit, so I've allowed myself to walk a little bit around and see other stuff around. But that's essentially where I am still. So this is what my talk is actually going to be. All right, so let me start. So there is a skeleta in the title. I don't really want to say anything about skeleta, because first of all, I don't know much. Second, I probably won't have time. But let me start with that at least. So this is, think about it as a motivation. So if you have a hypersurface Z given by some equation, Am is Z to the x to the m is in some lattice points of some polytope equals 0. Think of this as an affine hypersurface in C star to the m. So we know by the late 50s, Andreotti, Frenkel, Tom, so they said, all right, so this is a Stein manifold, so it's got to have a skeleton, and they actually gave us a description how you get at the skeleton. You just pick a point, take the distance function, take its stable manifold of its gradient flow, and that's your skeleton. Well, I mean, for practical purposes, it's probably not a good description. So, several years ago, I found this beautiful paper of Rudat, also promised to be here, Sibilla, Treumann, and Zaslow. We sort of describe the skeleta in a pure combinatorial terms, so let me just give a brief description so that you would know what we're talking about. So let me just give an example. So if we have a Newton polytope, which is sort of like this, so this is the origin, and this is 0, 3, cortex 2, and 3, 0, for instance. So looking at this Newton polytope, you sort of pick this as your origin. So everything, so it's triangulated. So there's a triangulation. So you looked at the simplices which are on the boundary of this triangulation. So this is your origin. So you look at the simplices T, which is in the boundary of this triangulation, and then you form the following abstract polyhedral complex. So if you look at, all right, so let me call it S. This is to be the skeleton. So this is a union of all strata in a boundary, and then you take this simplex itself and multiply it. So this, everything, all right, so this C star to the n for me is going to be R to the n cross R to the n 2 pi. Z. Zn. So the Newton polytope is in a dual space. So tau is in a dual space, and then you take cross something in the torus. And what you take in the torus, let me call it T tau chirp. And what is this? Is the set of points in the torus. So T, I got it right. Tn such that T, so if you take any vertex where is T, you get an element 2 by Z for all vertices, all V vertices. Okay, so let me just maybe draw a picture here. So for instance, this is your tau. So it has one vertex, 0, 3. So what do you take? You take actually, if you look at this, what's perpendicular to this vector in the torus, then we see the 3 tori. It's 3 circles. Same thing here, because this is not primitive vector, so it has point of order length of it. So it has two circles in a fiber, which is, and these 2 circles, so maybe it's the wrong way to draw it. Well, anyway, it's sort of perpendicular to this vector. And so over here you have also 3 circles here. And what about over the edges? Over the edges, if you think of it, or the edge are actually in a fiber of this edge. There are 6 points here, which are becomes integral once you multiply by both vectors 0, 3, and 2. There are actually six edges between these two. So, yeah, so every circle here is connected by an edge to the circle there. Well, 6. And similar also 6. So, all right. So this is what the motivation. I don't want to say some more about that. So question is where this skeleta live? Where do they live? Well, I mean, these guys are sort of very high tech. So they put it in some. So this S lives in some. I don't have any idea what this is. Kata Nakayama space. It's sort of some space coming from a log geometry, and they say this space is actually homeomorphic to the original hypersurface. So they sort of exhibit skeleta of the original hypersurface. Well, I have no idea. I mean, don't ask me about what this is. There is some, yeah, there is some log geometry. I mean, they consider actually a family of such things, and T goes to 0. There is this log geometry.
So they just take the space of homomorphism from the space to the polar log lines. That's the kind.
You probably know much more than that. So, but I'm very basic. I'm in this hole, remember? Very limited vision. Yeah, by the way, this hole actually, you can see a lot of things from this hole. Yeah, you do see this flora and everything. The interesting part, which you don't see, actually is, of course, it's in quadruple dimension 2. Right? So where you have this, I mean, this flora have monodromy, so there are some fibers which are very interesting. So I think this is still not understood very well. So I'm allowing myself to walk a little bit around. And this is where the tropical geometry, I mean, this thing evolved, of course, into tropical geometry, right? Very soon. When you look at the objects like that. So this is what I'm going to be looking at. So, right, so being spending a lot of my time thinking about tropical geometry, this is immediately, so tells me where this thing should live. I mean, not in any, kata Nakayama, something. So let me tell you what's the object they really live in. And it's very basic. So this is called a phase tropical hypersurface. So what does it? So okay, so I'll start with the same thing. So this is my affine hypersurface, and I construct this for a tropical hypersurface by taking the following functions, so taking the maximum. So Denis already spoke of this, and I guess many of you have seen it before anyway. So let me just write it down. So take m times x minus log. So this is a piecewise linear function, convex piecewise linear function. It's given by a maximum of a bunch of linear functions, and you take its corner locus. And then you see this polyhedral complex, which we call, let me call it T. Oh, it's Z. So let me call it X. So we have this tropical variety which lives in Rn, this corner locus, and it's a weighted, balanced polyhedral complex. So this is not the end. I want to enhance it by putting some fibers over it. And the fibers are going to be, so put fibers. So the fibers over its strata, the following. So the strata are parameterized at first. This complex is dual to the, or maybe I'll say, what? So if you have this this function log am gives you a function on your Newton polytope. So this function, taking its upper convex whole, gives you the triangulation of your Newton polytope, and the strata, of course, in this corner locus are dual to the faces of this triangulation. So if you take a tau here, there is a corresponding stratum here. So let me maybe draw a picture in this case. Dual to this triangulation. So if you take tau, this is a dual stratum tau here. So what lives over this stratum? They're co-amoebas. So these are amoebas. These are co-amoebas. What are the co-amoebas? I'll tell you in a second. But the co-amoebas of the following hypersurface. So you only take from this sum. You take only the monomials with which are vertices of this tau. So M is a tau. I'll give an example in a second. So what is co-amoeba? So surprisingly, there are no co-amoebas in a GKZ book. Only amoebas. So if you have an argument map from C star and to the torus Tn, and if you have something in here, so any hypersurface V in here, you just take the argument of this V, take its closure, and call it the co-amoeba. So it's a subset of the torus. It turns out to be, for hypersurface, this is a polyhedral thing. So this is a polyhedral complex, full dimension. Before telling you what it is in general, let me give an example. What is going to be in this case? maybe I'll draw. Over the edges, the fibers are just circles. So here is a circle which is parallel to this edge. Well, in this case, it's actually going to be 3 circles. It's exactly the same 3 circles over there. Because over this edge, what's the equation I have to restrict to this edge? Well, if you look at this, well, let me call it 1. This is y cubed. This is x cubed. So if you want to on the fiber over this edge, you just look at two monomials, 1 plus y cubed equals 0. If you look at the co-amoeba of this thing, what y can be, well, we know that y cubed is equal to -1, so the argument of y cubed has to be, I guess, pi over 3, pi, or 5 pi over 3. An argument of x can be arbitrary. So there are 3 circles over this edge. Let me try to draw a picture over this vertex here. So this is my torus. I have 3 fibers like this. Pi, pi over 3. So this is from 0 to 2 pi. This. I have fibers on this. This is 1 fiber. So there are 3 vertical circles. There is 1 circle which is kind of parallel to this edge, and there are 2 circles parallel to this edge. Try to draw. So if you look what actually is in the image, you see this kind of pattern, this triangle. Well, I picture it better up here. So what's shaded is in the image of the argument. So, in general, what's the co-amoeba? So some people would like to draw it from the -pi to pi. And it's easy to say, it's easy to draw, it's kind of useless. And this is where people mostly draw it from -pi to pi, because so you can look at that's the co-amoeba. Yeah, maybe okay. Let me say what's in so theorem. I think it's true, though we haven't written it down. So we prove this curve the following. So if you look at this tropical space, tropical hypersurface space. Hypersurface. Then it's homeomorphic. To the original complex. So I think, well, all my life I thought this is obvious. There is a little bit of history here, so I think everybody assumes it's obvious. I mean, all I've seen some symplectic calculations that are actually done in this tropical hypersurface, in a phase tropical hypersurface. But my experience also working with this polyhedral type object, it looks obvious, but you can't prove it, and it's probably not true. If you can prove it easily. So, Vero actually made it, so there is a polarizer to this, which is, Vero wants to claim it's his conjecture, so okay. Conjecture that this phase tropical thing is a topological manifold. So how can I originally didn't believe it? So there was some discussion, and you'll see why. So it's sort of, it looks very plausible. So let me say let me give an example. This is actually the only needed example. So it's a pair of pens. Yeah, maybe before giving an example, let me say okay, so there is more than just homomorphism, of course, right? So because if we want to do any symplectic Fukaya type for calculations, this is a space you want to work on. And so you can see some Lagrangians in there and stuff like that. Maybe. There is one thing which I can say about this homeomorphism. It's not just homomorphism. I've learned from Carlos talks this week. P equals W. So let me see it what it looks like to me. So you can compactify everything. So there is a compact version of this. So say projective version. This, and also you don't need really X to be a hypersurface. X can be any projective variety. Projective family. So let me say it's actually a family of a punctured disk. This delta is not that delta. Punctured disk. Then here is a theorem which is true, which we proved with Ittenberg, Halkin, Zharkov, Halkin. The following, you can take a limiting mixed Hodge structure of this and take the Steinberg-Kelly spectral sequence. The spectral sequence and take the E1 term in there. So the Steinberg-Kelly spectral sequence is known to calculate the wave filtration in this limiting mixed Hodge structure. So, and on the other hand, you can take this obvious projection from the phase tropical variety to just the tropical variety. And then you can take the array spectral sequence, and you can take the one term in the array spectral sequence for projecting phase tropical to just the tropical X. And I agree. Well, not quite. They're quasi-normal. Both degenerated FE2 and Kazarov complex, they're quite isomorphic. So this is my understanding of P equals W.
P and W.
P is, I mean, this is period thing. This is P, and this is the base iteration, this is W.
But they're on the same space. Huh?
They are on different spaces which are homeomorphic.
Oh, that's
Any questions? So here is my main example, which I'm going to do. So I hope I will say two interesting things. I think this was one interesting thing, and I hope I'll say another one. So here is an example, which is the main example. It's a pair of pens. So what's a pair of pens? One, which is, my one is actually going to be x0. x1 plus xn equals 0. So n equals 2. That's the only thing that we can draw. Yeah, I forgot to say it. Maybe since I'm 8, I don't want to say the wrong thing. So here is the condition that the tropical limit is smooth. Right. I don't think it's necessary condition. You can probably lift it, but the way we proved it. Which means, roughly speaking, that your tropical variety is sort of matroidal. So at every vertex you have like a fan, and this is a matroidal fan. And then this elements, I mean, this cohomology of the fibers are essentially the cohomology of the hyperplane, of the complements of the hyperplane arrangement that is calculated by the Euler-Solomon algebra. So which you can actually describe, you know, purely in tropical terms. So you don't really need to consider this phase. All right, so back to the pair of pens. So, all right, so on the other hand, we see this picture over, you know, we have a curve, tropical line, so you know what this is. So what we see on this tropical line, well, we see that here we have a circle fiber. Here we have this fiber given by the, let me draw it like this. And again, this is from 0 to 2 pi. This is the coamigo of 1 plus x plus y equals 0. So what you see is that in the middle you see two triangles like this. Let me try to draw it over it. So there's a triangle here. There's a cylinder going this way. There's a cylinder going this way. There's a cylinder. And obviously, you just see this pair of pens, this is pair of pens. Yeah. So we think that this theorem is obvious, absolutely, in this example. Well, this is actually deceiving example. This is the only example when the fiber in the middle is full dimensional. In general, if the fiber is n-dimensional, the whole space is 2n minus 2 dimensional. So it's not even half dimensional, so it's a complicated thing. Let me draw the picture n equals 3. Well, let me try to draw a picture. And then you use your imagination. This is a 4-dimensional space. But already on this one, it's not clear this is a topological manifold. All right, this is a tropical hyperplane in R3. Make sense? What will they draw? Everybody knows, right? So this is a dual to the simplex. It has 6 facets, it has 4 rays and a vertex. So of course the most complicated stuff is in here. let me try to draw the co-amoeba. This is my cube. I practiced it several times yesterday evening. So on each face it looks like the two-dimensional picture. And I didn't practice enough. But imagine, on this face you have this two-dimensional picture over there, and take the cylinder into the horizontal direction. Same thing for the vertical one, you take the cylinder over there, and from this one you take the cylinder, and then take the union of all the things. You can also take the cylinder into, along the main diagonal, which correspond to the fiber over this edge, but that's already included in the union. So use your imagination, that's what it's called. Deceivingly simple way to describe this co-amoeba is just to take this is co-amoeba of the pair of pens. Pair of pens, let me call it PP. Co-amoeba of the pair of pens is the complement of the following zonotop. It's given by equations like theta I minus theta j x less than 5 for all I and j. Thinking about my theta 0 being 0. Thetas are the argument of the coordinates. So it's a complement of this beautiful zonotop, and this is usually how people draw it. I wanted to do, but that's picture from minus pi to pi. I really want it from 0 to 2 pi, and you will see in a second why is better. Okay. So how would you prove this main theorem? Well, essentially, there is this pair of pens decomposition for hypersurfaces due to Mihalkin, for complex hypersurfaces. So if you have a complex hypersurface, you can decompose it into pair of pens. And there's an obvious pair of pens decomposition on the tropical side. You just take, the neighborhood of the vertices. So they're very much, compatible. And this would be it for the if you had a unimodular triangulation. If it's not unimodular, like in the first example I gave you, this is just a covering by the ordinary pair of pens, with the degree given by the volume of the simplex. So the proof of the theorem is essentially boils down to just proof of the theorem for the pair of pens. So this is what I'm so what I'm going to do, I'm going to give two CW decomposition of the two. So we have a pair of pens, a complex pair of pens, and we have a tropical pair of pens. Both of them map to the co-amoeba, but just by taking the argument maps. So I'm going to give a CCW decomposition based on some decomposition of the co-amoeba into polyhedra. So what's the decomposition in the polyhedra? So I'm going to decompose the co-amoeba into, well, let me call it octahedra, because this is what they are in dimension 3. Well, in dimension 2, there are these two triangles. This is my decomposition. In dimension 3, there are going to be 6 octahedra, so let me first maybe draw them on this picture. Try to draw. All right. You take this square and you take this vertex, the pyramid over the square, with this vertex, and you take the opposite vertex, take the pyramid. There are 6 of those octahedra. They fill the full Colamoeba. What they are, given an order of the phases, ordering. So let me call this order sigma. Is given by 0, which is an argument. Well, let me call theta 1. Already used it. Theta 0. Then theta sigma 1, theta sigma m. So I order the arguments of my variables. So what does it mean? It means that if I draw the, all this clockwise, counterclockwise direction, so this is my 1 vector, this is my x sigma 1, this is x sigma 2, this is x sigma 3, x sigma 4. They form a convex polygon, and that's what I'm going to fix. I'm going to fix the labels for this vertex. So there is precisely n factorial ways to do it. N factorial ways. So in the case of n equals 3, it's 6. In the case of n equals 2, 2. The intersection between the strata, of course, when we show the smaller strata, when I allow some of the inequalities become equalities, so some inequalities become equalities. So it means that I'm allowing to have, what's intersection, for instance, would be if you have a x sigma 3 and then x sigma. They are sort of, I have a less number of angles. So, all right. So what I'm going to do, I'm going to pull those back to both spaces, here and here, and I get cell decomposition of both spaces. What I claim, since they come from the same cell decomposition of the Colamoeba, they are isomorphic as a cell complexes. So what I need to prove now, and this is the main part of my talk, they are actually regular polyhedral. They are regular cell complexes, and then we are done. And this is actually the main technical difficulty. All right. So maybe I'll say a word about, if you look at the vertex, for instance, this vertex over here, this vertex over here, what's the vertices correspond to? The vertices correspond to, all but one sign being, equality here. So it means that your polygon is sort of very degenerate. You have a bunch of arrows, right, and then you have a bunch of arrows left. So in other words, these are the pullback of the vertices are the real loci of this. So the vertices. So let me say this. This is called them phi sigma. Yeah, so this is phi sigma. So the pullback of the vector dynamic has this maps phi. Phi looks like T. Argument. So argument inverse of the vertex is real. All right, so how many vertices I have? I have 2 to the n minus 1 vertices. It's the way how I'm going to split my n plus 1 variables into bunch of positive and bunch of negative. So 2n minus 1. 2 to the n minus 1 ways to do it. Oh, okay. All right, so here comes 2 lemmas, which are enough to prove everything. So I'm skipping a little technical thing, so I really need to compactify both my spaces because I want to, compare two close polyhedral subsets, two close cell complexes to make them homomorphic. So how would you do this? So compactify tropical pair of pens is just compactifying. It's sort of linear at the infinity, so this will just add this boundary. How would you compactify a pair of pens? Of course, you don't want it to compactify into projective space. This would be certainly different. So it's sort of the idea is to leave these circles to being on the boundary. So compactify this pair of pens. So you don't want to compactify it in projective space. You compactify it you take a tropical projective space, and you still take the full torus fiber over the boundary component. So you don't want to compactify this puncture by just a point. You want to compactify it by leaving it a circle. All right, so what does it do with, all right, so lemma 1 and lemma 2. Depending on how much time I have, I'll explain key features of lemma 1. So lemma 1 is that, this P sigma, which is pullback to P sigma, is the argument inverse. So this P sigma is a regular CW complex. And lemma 2, so it's the same thing, only 2 here. And here we have T P sigma. Let me say let me say a word about lemma 1, because I have a conjecture, like polytopes, that may be for you. So, what is the space we are dealing with here? We are dealing with a modular space of polygons, compactified in the following way. So, what is the lemma 1? And I couldn't find a reference for this, so there are various compactification spaces for the polygons. This one I have not seen, so if you know any reference, let me know. So you modulate space of polygons, convex polygons, So what are allowed degenerations? You allow length to be 0, length. All right, so modulo, of course, up to scaling and rotation. Because we really can multiply all the variables by a complex, non-zero complex number. Allow length of edges, edge goes to 0. While doing so, you still keep the angle. Keep the angle in mind. It's kind of hard to draw as a polygon. For instance, if you have a triangle, you can have this edge to be very, very small, sort of 0, but you still, so it looks like this, so only 2 edges, but you still remember the direction of this edge. And in a sense that it still has to be convex. So this direction of this edge, it may be very horizontal, maybe sort of vertical, but it's sort of, the direction of the stage is between this theta 2. Theta 2 is between phi and 2 pi. Does that make sense? And you allow, of course, so this is the first thing, and then you allow angles to go to 0. The angle for me is not this angle, of course. It's the angle between these two vectors. So in some sense, you allow 2 consecutive edges to to become parallel. It's 2n minus 2-dimensional if it's a. All right, so we have a n plus 1 gone. N plus 1 gone. It's the dimension is, or dimension of this thing, 2n minus 2. So for the case of, so maybe give an example, n equals 2, then it looks like a hexagon. So the vertices are the maximally degenerate ones. What are the maximally vertices? Are the following. So you degenerate your polygon, as much as you can. So what you can leave, you can have all the, edges. Some of the edges to be, one direction, and some of the other. I mean, all the remaining edges, going backwards. But only 2 of the edges have non-zero lengths. So in some sense, well, the picture looks like this. So you have a non-zero length edge, then you have a lot of zero length edges. Maybe some of this side, and also backwards, the same thing. So you have one non-zero length edge, and then lots of zero length edges. So the vertices would. So okay. So if I'm to do combinatorial picture of this, so I have to mark the edges. I have to mark the vertices which are zero angle, and I have to mark the edges which are zero angle. So this one I can mark, for instance, this one I can mark. So mark zero length edges and zero angles. And what's left? What's left are 2 unmarked edges. They have to be 2, right? Because I have to go back. I mean, I have to go. I must have go if one is like that, then I must have another edge like that. And I must have two non-marked vertices between these two edges, because this is where I'm allowed to have, the bend. This bend is supposed to be, pi. But so I have to, one unmarked, so unmarked here, maybe one unmarked here, and I have to have, unmarked vertices in between them. So the picture should be like this. So I have a unmarked edge, and unmarked vertex, and unmarked vertex between them. Everything else I can mark. So this is a phase lattice of my moduli space. Here's conjecture for those who love polytopic. This is this is a phase lattice. Conjecture. It's a phase lattice of a polytope.
Can you repeat this? So what will be the vertices of this polytope? How many vertices?
Vertices, all right, so how many? It's hard to count. I think I gave this as a combinatorial problem to my combinatorics class. So the vertices are the pairs. Okay, so let me say vertices are pairs of vertices and pairs of edges, which are in between those vertices.
Oh.
And then you add. After that, this becomes Boolean. You just add anything in your.
The angles have to be maximum at these vertices.
Huh?
The angles at these vertices have to be maximum.
At the vertices, they're forced to be maximal because. But you don't force them a priori. They just by themselves. So if you look at this n equals 2, that's an answer. This is a hexagon. So there are actually 6 vertices because in a triangle you have to pick a vertex and an edge, so that the unmarked ones form like this. So that vertex and edge have to be adjacent. So there are 6 ways to pick pairs, vertex, edge, adjacent pair in a triangle. N equals 3. It took me a while actually to find a polytope. It would be fantastic if somebody finds like a realization in 2n minus 2-dimensional spaces. Misha likes such things. Right? This is sort of this secondary polytope. All right, so n equals 3. All right, so we have 8 vertices. Sorry, 8 faces. I can even draw the faces. So the faces are dimension 3, so I can draw them. The wedge of 2 hexagons. Wedge. 2 hexagons. And so there are 8 faces like this, so there are 20 vertices. And the polytope hypothesis is simple, right? Because once you fix a vertex, the face lattice which contains this vertex is Boolean, right? So this is a simple polytope. It has to be simple. So find a simple polytope with 8 faces like that and 20 vertices. So what I did, I actually looked at a dual polytope. The dual polytope is simplicial, so dual one. Dual polytope. It's simplicial polytope with 8 vertices. Simplicial polytope. 4-dimensional polytope. 4-dimensional. And luckily there is a paper, Greenbaum and Greenbaum, Hanan, 67. There are 37 simple simplicial polytopes with 8 vertices, 4-dimensional. 37 of them classified. And this one has a number 35. So, all right. All right, so I have, how much time I have? Nothing? 5 minutes. 5 minutes? All right, so let me make another thing which you may like. So let me not go into technical stuff. Let me just maybe say one, I think, other combinatorial object which comes out of this thing, which I've never seen before, again, tell me if you have. All right, so let me just tell you how the proof of this lemma goes. Once you have it, then the interior of the polytope is clearly a ball. I mean, it's you don't just start building your polygon with non-zero angles and non-zero vertices, and then you see that at each point for the next vector you would have, you know, inequality in R2 of choices. So every time you do this, so this next vector cannot go, you know, over here, so it has to go here, and it cannot go in this part, and it cannot go in this part. So anywhere in this part, it can land. So at each step, you have a two-dimensional polygon, open polygon of choices. So this is a ball here. And then the thing is to show this is actually a closed ball, right? This is what makes it difficult, right? So why is it a closed ball? Again, so near the vertex, you just look at the coordinates. The coordinates are very easy to find. If you have a vertex, so this is a very long diagonal, and then somewhere you have a non-zero edge and another non-zero edge, and your coordinates are just the relative lengths of the other edges and the angles between those edges. So this is a 2n minus 2 coordinate for the vertex. So this is a closed ball. That's all we need. So this becomes a regular CW complex. On the other side, I have 3 minutes. All right. So you subdivide this thing. So this is not a polyhedral complex. If you just pull back this octahedra to the phase tropical variety, this is not a polyhedral complex. But you need to subdivide this octahedra into alcoves. So alcoves. What's an alcove? Alcove is given by the, so it's a subdivision by you know, theta I minus theta j being in phi z. So each octahedra is actually subdivided into 4 tetrahedra. So I won't draw it, but anyway. So it's a 4 octahedra, and now you kind of and now you pull back those alcoves. This becomes a polyhedral complex. Then to show that this polyhedral complex is a ball. Again, so it's not very hard. You just give sort of a meshing on a phase lattice. So it sort of it gives you it's a collapsible regular polyhedral complex. It's collapsible regular polyhedral complex. And then the hard part is to show this is a manifold. Once you show this is a topological manifold, you're done. This is a ball. And this is where Kerr actually came up with this very beautiful idea how to show this is a topological manifold. But anyway, so 2 minutes, and I'll just say one word about combinatorics, which I like a lot about this thing. What are the alcoves? How they parameterized? So alcoves are indices indexed by the following. So if you take a polygon, you take a set of diameters. So who is the diameter? Diameter is a diagonal, maybe a side, so that if you can draw your polygon between, you know, in a strip, so that the picture is like that. So this is the diameter. There are n plus 1 diameters. For the n+1 gone, there are n+1 diameters. Every 2 diameters intersect. So this is a new object in combinatorics, which I propose. I haven't seen it. I talked to several, to several configuration spaces people. They never heard of this. So let me tell you, and maybe somebody told me. It's diameters. Sets of diameters in an n+1 bond is the same as triangulations of the Möbius strip. So how does it work? So if you have, for instance, let me just give an example. So what are the diameters here? So this is the diameter. So let me call A, B, C, D. This is not a diameter. This is not a diameter. This is a diameter. This is a diameter. This is a diameter, and this is a diameter. So there are 4 diameters here. If you draw it in a Möbius strip, so how you draw it? Take A, B, C. This is your Möbius strip. You have to cut it along some of the diameters, C, D, A. So this is the diameter, AC is the diameter, BD is the diameter, AB is not a diameter, but AD is not a diameter, CD is a diameter, and BC is a diameter. Okay, so this is probably, I think this is also a nice object in combinatorics to study. So if you heard of that, let me know. Okay, I'll stop here.
Any questions or comments?
So all this combinatorics is just for the case of the pair of pens, right?
Combinatorics of what?
So what you explained in the last 10 minutes.
Yeah.
It's just for the case of pair of pens.
The polytope,
Yes, polytope.
my conjectural polytope is the hexagon.
Yeah. Not for n-dimensional pair of pens.
For the n,
For the n-dimensional pair of pens. For the,
it's this Zharkov thing. I mean, if you know this AN story, this is sort of decomposition of the into alcoves and minus sort of the alcoves which have a vertex at the origin. I mean, it's combinatorics, yes. I mean, I think the combinatorics of this triangulations of the Möbius strip is not very interesting.
So the statement is that the structural pair of pens are topologically connected?
Yes, this is a corollary. It's actually homeomorphic. It's more than that. It's homeomorphic to the actual pair of pens. And all these Lagrangian spheres, like we see here, like
Is it embedded as a submanifold, as a pair? Like C star to +1?
I think that's not a problem.
That you don't know.
Yeah, I just prove it as they are identical as a regular CCW complex. You may want to subdivide it more to have all this. If you want to work with the Lagrangian object, maybe I'll say one word. This real points, of course, are. I mean, the original motivation would be to see Lagrangian objects in a pair of pens in this tropical pair of pens. So how would you see them? So and you do see somewhere. You see the real loci there, and you see this Seidel Sheridan's immersed, spheres as just a boundary of your colony. But you may want to see more, for instance. So for this, you have to subdivide it, fine.
So is there any way to connect this Möbius strips with the description of tropical variety?
Haven't thought about it. Probably not. I mean, prime varieties is kind of a very rich structure, so this is very simple.
Okay, so if there are no more questions, then the speaker